Mr. Tima here. Going to start our gravity in free fall notes. This is part 1. Okay, here we go. Look at that guy. Isn't he having a good time? All right. So on gravity on Earth is constant. It is measured to be 9.81 meters per second squared. Now it can be positive or negative. We tend to think of it on Earth as negative due to the fact that we usually hold something out in front of us and we usually use the ground. Okay, not as the 0 point, but where our hand is as the 0 point or the origin, and the ground in the negative direction. So we tend to think of it as negative, but it can be positive or negative depending upon that. So, quick question. If I have a ball here and a ball here, and I drop a ball at the exact same time that I shoot a ball, which one's going to hit the ball? Which one's going to hit the ground first? Which one's going to hit the ground first? Do you think it's going to be A, the one that's dropped? Or do you think it's going to be B, the one that hits the ground? Or that's launched, excuse me. Do you think it's A, the one that's dropped, or B, the one good night. The one that falls, or B, the one that's launched and shot out? Well, let's look at this video and take a look. He likes to show himself setting up. So if you said they were going to hit it exactly the same time, you were right. Then he likes to take it down. Let's watch that one more time, though. Let's watch that one more time. I'm going to stop it right there. Not only does it hit it exactly the same time, you can hear it with sound, but also watch the second hits. And the third. Boom. It's the same thing. It is the same thing over and over because of the acceleration due to gravity. Okay? They are hitting at exactly the same time. And that's because the balls are falling at the same rate. The ball that's dropping and the ball that's shooting fall at exactly the same rate. It doesn't matter. This is a time stop photo, and you can see that they're falling at the same rate. It doesn't matter how far they go out. So that leads us to the classic Mythbusters. Okay, the classic Mythbusters example is, all right, if we fire a bullet and we drop a bullet at exactly the same time. Check it out.
Writing's not that easy, but Grammarly can help. This sentence is grammatically correct.
What you got there? This is a good one. Picture two bullets, each exactly the same distance from the ground, each released at the exact same second, except one bullet is dropped to the ground, the other is fired from a gun. The classic physics thought experiment states that both bullets will hit the ground at the same time. Based on what theory? Based on the theory that the bullet that's fired from the gun has no wings on it, no lift. Thus, gravity has the same effect on it as it does on the drop bullet, and thus they hit the ground simultaneously. It's an age-old physics fable that says a bullet dropped and a bullet fired simultaneously from the same height will hit the ground at the same time. But it's so darn difficult to test that no one's tried until now. So what's the plan? Well, I've been thinking about this one for so long. While I have seen this experiment elucidated in textbooks the world over, I don't think that anyone anywhere has ever tried it full size, full scale, with real bullets coming out of real guns. That's what we should do.
It sounds like it can be kind of tricky, actually. I think we should do some shop experiments before we start using any live rounds.
Fair enough. Let's start.
So before going ballistic with the ballistics, Adam comes up with a more simple way to put that textbook theory to the test.
Well, this test is going to be comprised of two separate parts, and I am using a bullet of sorts. You may recognize the steel ball bearing as some of our ammunition from Steam Machine Gun. Part the first. I will be dropping this ball bearing from exactly table height, handily marked by this green line right here. I'll be filming its drop on a high-speed camera and counting how long it takes to get to the ground. Part the second. I'll be shooting this ball bearing from my little pinball shooter here, which I've marked out to be really accurate every time I shoot it. And I'm going to fire it across the same branch and measure how long it takes to reach the floor on the same high-speed camera. If this myth is true, those two times should be identical. Okay, here we go. This is the drop from table height. In 3, 2, 1. Pretty simple.
Couldn't be simpler, but there's a lot more to this test than meets the eye.
Counting the frames of the high-speed shot, the marble took exactly 201 frames to get from my hand to the ground. And because we were filming at 500 frames per second, each frame is 2 milliseconds, which means that the total travel was 402 milliseconds. Or for those of you who love fractions, and come on, who doesn't? 4.02 tenths of a second.
So 402 is the benchmark. Now, how will the fired ball stack up?
High-speed ready?
Time for some pinball wizardry.
Here we go. Pinball shooter. In 3, 2, 1.
And the results are flipping fabulous.
What do you got?
It's actually pretty cool. When I drop the ball from table height, it takes 402 milliseconds to reach the ground. When I shoot it from this pinball shooter, 410 milliseconds to reach the ground. It's 0.8% difference. That's pretty much identical.
With less than 1% difference, that's a pretty powerful result. And a provisional thumbs up for the myth. But Jamie's not impressed.
Okay, but I thought the story was about guns.
You really want to get to shooting guns?
Well, yeah.
So we will actually watch the rest of this as we go forward into projectile motion, but we'll save that part for another time. So Newton's second law, free fall. To have free fall, we must have no resistance. Okay, no air resistance, or air resistance and gravity must be equal to each other. So on Earth, this doesn't exist. If we dropped an elephant and a feather off a building at exactly the same time, they should hit exactly the same time. But we know that that's not true. We know that the elephant will hit before the feather because something called air resistance. All right. This is found in a vacuum, though. And when we say vacuum, we literally mean like a vacuum of outer space. Technically, the vacuum you use at your house creates a vacuum, but we'll talk about that more. So what's really cool is there was actually an experiment done in outer space to prove this.
Jim, we copied both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. I have a good picture there. I've got
Beautiful picture, Dave.
well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about about that? Proves that Mr. Galileo was correct in his findings.
Oh my goodness, that beeping. But there you go. When you're transmitting from the moon, that stuff's going to happen. But it is kind of crazy. I mean, it's really science in action there to think that this is actually happening. It's falling at exactly the same rate. It's doing exactly what it's supposed to do. Okay. All right. As you've known by now, we've talked about SUVOT. All right. SUVOT are those equations that we need. Okay. Those are those IB equations. Now, what's crazy is with SUVOT, there was all those equations. There are 4 big equations. But here we go. Anytime we have to remember that SUVOT can be in the y direction also. I mean, this is just one-dimensional motion, but in the y direction. It's a drop. It's the same as if we were running and accelerating in the x direction. It's exactly the same thing. Okay? For example, this is the equation we're going to use a ton anytime we drop something. Because think about what we know. What is our starting velocity? What is our initial velocity? The answer is 0. Most times it's going to be 0 because it's held in our hand and then we drop it. Acceleration really is going to be called something different when we drop it. It's going to be called g, okay, for gravity, but it's still the same thing. G is just the acceleration due to gravity, and we know that as 9.81, and that is a constant. And now we either need to find the time or we know the time, or we need to find the displacement or we know the displacement. So again, this equation is something we're going to use a ton of. What do we have? What do we know? Sometimes we'll know the height of the cliff and we want to know how far or how long it's going to take. Base jumpers, skydivers, they know how far they're up in the plane or how far they need to jump off the cliff. Now they need to calculate how much time they have to open their parachute or anything like that. So yeah, this equation is really a lifesaver. No pun intended. All right, we're going to do this lab. You're either going to have to print this lab out at home because you actually need the physical copy, or you'll receive one in class. Okay, can't really do it on Kami because you actually need the scaled version of this lab. All right, everybody, we will see you next time. And remember, keep doing that science and make sure to have fun doing it. Talk to you later. Mr. Tima out.